Hi class, welcome back. This is ME 354 demo number 5, last one of the quarter. So you're almost done. Today we're going to be looking at the buckling behavior of two different materials, our 6061 T6 aluminum and our 836 steel. We're going to test 5 specimens of each material, ranging in length from 500 millimeters down to 45 millimeters. We use the Instron loan frame. We're back at the static frame. And we've got some fixtures installed here that will provide a fixed end condition. So the ends are constrained, and then we'll compress them until they buckle. We'll record all that data in our data acquisition system as before, and the class will be provided with that data. So let's get started. We'll take a look at the specimens first and go on from there. So we've got our buckling specimens lined up here. On the top is the 836 steel. On the bottom is the 6061 T6 aluminum. The nominal lengths are 45 millimeters, 140 millimeters, 240 millimeters, 340 millimeters, and 500 millimeters. The actual lengths will vary by a few millimeters here and there, but we'll measure those as we go and enter them into the program. If we subtract the combined grip length of 40 millimeters from those numbers, we end up with our unsupported length. So I pulled the grips out of the machine so we could have a closer look. Pretty straightforward. One end's machined to fit into the Instron grip adapters. The other end is just a solid cylinder with a 20 millimeter deep pocket machined in. And then we've pressed in this drill bushing here, so we have a hardened sleeve at a precise diameter of 6.35 millimeters or quarter inch. So our specimen slides in either end. One end fits into the base of the machine, the other end fits into the load cell. I'm going to mark this real quick so we can take a closer look at the specimen. Pull these off. And I'll zoom in. So here's our grip region, 20 millimeters long. So this area here at either end is constrained from translation in X and Y and from rotation. The region between is what we call the unsupported length. So we're ready for our first test. I'll start with the longest aluminum specimen. Drop it into the lower grip. So I'm fully engaged. I can drop down the crosshead. So I'm almost touching. And now I'm going to raise up the specimen so I'm engaged in both the upper and the lower grip. Jog it down a little more until I'm fully captured. Now I'll go ahead and mark the interface of the specimen and the top of the grip. Now I can raise it up fully engaged in the upper grip and jog down. This gives me a target so I can lower the crosshead down without overloading the specimen and prematurely damaging it. All right, I'm back over at the computer now. Got our specimen loaded up. Make sure we have a slightly positive load. I'll zero our extension. Now we'll enter our user inputs. This is the longest aluminum specimen, so I'm going to call it AL500, referring to the nominal 500 millimeter length. I've already measured the aluminum specimen diameters. They're all 6.34 millimeters. The actual measured total length is 502 millimeters. So our unsupported length is going to be 502 minus 40, which is 462. And we are just about ready to test. Zero our extension, and here we go. So this should buckle fairly soon, given the length. Our initial length looks fairly linear. If you keep an eye on the window at the bottom right, You can see that the graph has rolled over and the specimen is clearly buckled. It's clearly visible that the specimen is no longer vertical. So I'm going to stop the test. That's actually all the data we need to do the analysis for this lab. All right, I can go ahead and pull that out. It's difficult to see this, but if I spin this specimen, you can see that it's not actually plastically deformed. It's still straight. So we didn't actually damage the specimen. It just could no longer carry the load. All right, we'll move on to the next aluminum specimen. Go ahead and drop it in. All right, and our user inputs. AL340. Our measured total length is actually 339. So our unsupported length is 299. And 0R extension. And we are ready to go. So we should get a higher load now before we see the buckling initiate. Let's see what happens. As expected, this is going to take a little bit more load before the buckling will initiate. Looks like it's clearly no longer vertical. And so we've buckled. I can go ahead and stop the test there. All right, we'll pull this one out and we'll run through the rest of them and then move on to the steel. All right, so we finished up our aluminum specimens. Here's the plot for all 5 of them together, starting with the longest down at the bottom and the shortest up at the top. Notice that there's a little bit of a difference between the way they transition from linear to nonlinear. Let's move on to the steel. So that's it for the steel specimens. The plot here is showing just the steel. So I've laid out our test specimens here. Steel on the top, aluminum on the bottom. Some observations. The aluminum specimens, the two longest ones here, look to be straight. So even though we clearly buckled them, as you can see in the video, they have sprung back to their original shape. So they must have been in the elastic region the whole time. The middle two, however, look to be plastically deformed. They've retained their buckled appearance. But the shortest one is straight again. Same thing with the steel. The middle three are plastically deformed. Hard to tell on the longest one. Possibly is plastically deformed. But again, the short one appears to be straight. So food for thought. Well, that's it for this lab and for the quarter. You'll receive a data set in Excel format of all 10 specimens. Thanks for hanging in there with us. I know it's been challenging. Hopefully next year will be better. Thanks for watching.